Have you ever looked at one of those beautiful ancient patterns and wondered if there's something more to it, like a secret code hidden inside? Well, what if I told you there is? And today, we're going to unlock it. We're going to dive into a system where simple, everyday numbers reveal the hidden rules of incredibly complex shapes. Okay, let's get into it. Okay, so take a look at this. It's this gorgeous, intricate diagram. You might recognize parts of it. Right in the middle, you can see a shape called the seed of life. It's just made of these perfectly overlapping circles, and it feels right, it feels harmonious. But what if that harmony isn't just a cool design? What if it's actually following a very strict set of rules, like a hidden language just waiting for us to crack the code? And what if I told you the key, the Rosetta Stone for this whole thing, isn't some crazy complex formula from a university textbook? What if it's something you've known your entire life? Yep, the 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Turns out there's a secret rhythm, a hidden structure, in how these numbers relate to each other. So, our first step, we have to forget the shapes for a second. We're just going to look at the numbers themselves. Think of it like we're building a secret decoder ring. And the cool part is, we're not building it from geometry, we're building it from a special pattern that's been hiding in our numbers all along. So here's the big idea. It all comes down to how we arrange things. We're not doing any heavy-duty calculations here, not yet anyway. We're just looking at the order of the numbers. We're about to find a structure that's just part of what the numbers are, before we ever try to draw them on a circle or a square. Okay, so this slide breaks down our decoder ring. First, look at the team. We just split our 10 digits into two groups. You've got the main group, let's call it the engine, which has the numbers 2 through 9. And as you can see, this group follows a really specific 8-step loop. 2 goes to 3, 3 goes to 4, then to 6, 5, 8, 7, 9, and then bam, right back to 2 to start all over again. Our other little group, the flip switch, is just 0 and 1. They're simple, they just swap places with each other. That's it. So if we take our number engine and we run it exactly halfway, that's 4 steps, something really cool happens. Every single number lands on its opposite partner. 2 swaps with 5, 3 swaps with 8, and so on. They're called antipodal pairs, which is just a fancy way of saying they're on opposite sides of the cycle, kind of like how the North Pole and the South Pole are opposites on a globe. This gives us these 4 fixed pairs that are linked together in a really fundamental way. But wait, you might be wondering, did we just make these pairs up? Is this random? And the answer is no, not at all. It turns out these specific pairs have unique mathematical properties that you wouldn't get if you just paired them up randomly. This proves the structure isn't something we invented. It's a property of the numbers themselves. The whole point is that the system is totally rigid. There are no random parts. The rules are baked right into the numbers. All right, we have our decoder ring, we understand the rules. Now for the fun part. It's time to actually use it. Let's take this abstract number pattern and see what happens when we apply it to a real geometric shape. So, our first test case is this 4-circle pattern right here, what this diagram calls stage I. It's simple, it's elegant. So, what we do is we map our numbers onto it. You can see the 8 numbers from our engine. The 2, 3, 4, and all the rest, they're placed on the 8 little outer regions in the exact order of their cycle. And our little 0, 1 flip switch pair, they go right in the middle in that space where everything overlaps. And here it is. This is the big aha moment, right here. All of a sudden, the abstract rules we made for our numbers become physical actions you can do to the shape. If you rotate the diagram by 45 degrees, that is exactly the same thing as taking 1 step forward in our number cycle. If you mirror the shape, like reflecting it in a mirror, that's the same as swapping one of our opposite pairs. The geometry and the arithmetic, they're literally speaking the same language. And here's what's so cool about that. The shape itself looks like it's based on a square, right? But the number system we've laid on top of it reveals a much deeper symmetry, the symmetry of an octagon. In math, we call the rules of an octagon D8. So it's like the numbers are showing us this hidden layer of complexity. And remember that little 0, 1 switch in the middle? Since it can flip on its own, it has its own separate symmetry. So when you put them together, you get this total symmetry that mathematicians call D8 times Z2, which just means you've got 2 independent systems working together perfectly in one diagram. Okay, that was amazing. Seriously. But what happens if we take our decoder ring and apply it to an even more intricate pattern? Let's level up. Let's see how this whole system handles the famous seed of life. So the seed of life has a central circle surrounded by 6 others, which gives it this beautiful hexagonal, 6-sided symmetry. We'll use a subset of our numbers for this one, 6 of them for the outer petals, and our trusty 0-1 pair goes right in the center again. We're applying the same core ideas, just in a brand new context. So visually, what do we see? We see the symmetry of a hexagon. 6 sides, pretty straightforward. But just like before, our number system is about to unlock a hidden layer of order, something way more profound than what you can just see with your eyes. This deeper pattern is a version of a concept called triality. Now, I know that sounds super complex, but stick with me, because it's actually a really beautiful idea. Normally, we talk about a shape having symmetry, but with triality, it means the rules of the symmetry themselves also have their own pattern. It's like a symmetry of symmetries, a pattern within the pattern. Let's make that super simple. If you look at step 1, turning the shape 180 degrees creates 3 pairs of numbers that swap places. Let's just think of them as 3 light switches. Switch 1, switch 2, and switch 3. Now look at the action. If we rotate the whole shape by 120 degrees, something incredible happens. It doesn't flip the switches on or off. No. Instead, as the final step shows, it perfectly rearranges the switches themselves. Switch 1 moves to where switch 2 was, 2 moves to 3 spot, and 3 cycles all the way back to where 1 started. That is triality in action, a symmetry that acts on other symmetries. So cool. So, okay, we've decoded 2 patterns. We've uncovered some really deep, really cool mathematical ideas. But what's the bigger picture here? I mean, why does this connection between simple numbers and complex shapes actually matter? Well, what's truly profound and kind of mind-blowing is that this system scales up. The same simple rules we started with, what the source material calls the C.O.R.E kernel, can be used for even more complex patterns, like this multi-layered flower of life you see here. The same simple number engine can describe the symmetries of a hexagon and even a dodecagon, all working together without adding a single new rule. The foundation is just that solid. So what should you take away from all this? First, that abstract math you learn in school, it's not just a bunch of problems on a page. It's a powerful language that can actually describe the real world. Second, that unbelievably complex and beautiful things can come from very simple, elegant rules. And finally, this whole thing gives us a hands-on way, like a toy model, to play with huge ideas like triality, concepts that are usually stuck in the world of advanced physics and makes them something we can all understand. And that leaves us with one last thought to chew on. We just unlocked a deep mathematical structure hidden inside the numbers 0 through 9 and a few common shapes. It really makes you wonder, doesn't it? What other incredible secrets are just hiding in plain sight, in the numbers and the shapes that surround us every single day?